Hello, everyone. My name is Liang Wang from Baidu USA, and my team is Robotic and the Auto Driving Lab. So today, the topic I'd like to share with you is NavDog, Robotic Navigation Guide Dog by Model Predictive Control and Human Robot Modeling. So first, let me introduce the background and motivation. For vision impaired people, they need guide dog for their daily life. However, to train the animal guide dog is very costly and difficult. To improve the vision impaired people's daily life quality, we developed this project to trying to get some research result. So for human robot guide dog modeling, which is the key idea here, so there are many similar situations such as bicycle model. However, this kind of model is not the best way to describe human guide robot system. Because for the bicycle model, they have a no sleep condition assumption, which means the rear wheel will not just have the rotation, but without velocity. However, in this case, the human can be pure rotation without the velocity. So we developed this simplified system kinetic model for this. Our system state representation is like here. We have our state vector have 5 elements. The B is represent for the robot, for the bot, and H is represent for the human. So this is considered in 2D situation. So X, B, Y, B are the position of our bot. XH, YH are position for the human. And theta B is the heading of our robot. So our control just gives the control to the robot. So we have 2. V is the velocity and omega is angular velocity. So let's just consider the robot here. So for the robot, it can be modeled as a unicycle model. So these first 3 equations are the updates of the states. The new position is based on the current position and the velocity and angular velocity. So the key part is how to estimate the human position in next step. Let's look at this picture here. So suppose our robot and human has a rigid rod connection. The rod length is R. So we assume that human and robot always keep the distance R. And if the robot goes straight, it will be simple. Now let's think the robot goes to another direction from BK to BK plus 1. And suppose human is still at this place, and the human will be guided by this rigid rod and to turn a little bit left. However, it also needs to keep the distance R. So we select this point as K as HK plus 1 as estimation of the human's position. So in this equation, D is the distance of HK and BK plus 1, and R is just their distance. So by using this kinematic model, we can update humans' position in these 2 equations. And for details, you can check our paper. Then we move to system design. The system have 3 components: perception, planning, and control. For the perception module, the input are the pre-scanned map and the destination. And the robot position measurement is from AMCL algorithms. And for the map, we use Gmapping to pre-define the map. And we also have obstacle detections using the LiDAR information. And we also use the LiDAR information to measure the human's position. And after these, it goes to the Kalman filter. Then it can output the system states, which is a 5 elements and the surrounding obstacles. And for the planning, It has the laser scan odometry as the input, and they have the system states and obstacles. We have global grid map generation, and we use graph search based method to generate the reference path. And then all this information to our MPC controllers. It has a local initial goal state generation, has a local grid map generation, which is considered the obstacles based on the map. And then MPC calculates the control commands and gives to the human robot system. So I'd like to mention one more thing about the MPC controller here. So basically it is an optimization problem. It can minimize this cost function, which is the control efforts, includes the control efforts to drive the current state to the final state, which subject to these constraint. The constraint includes the initial constraint and the kinematic model and the limits of their states. And this is for the obstacles avoidance. Yeah. And then I like to share our experiment results. We have simulation and real. In simulation, we have a simple room, and the start point is at the top right. The red dots represent for the robot, and the green dot represent for the people, and their connection is rigid. So this is the start point, and this is the end point. So you can find a path through to reach the destination. And you can see that can deal with the sharp turns. And in this case, there's some unknown obstacles here. So the algorithm is able to adjust this path to reach the destination for the people. We also compared this with the bicycle model, and the bicycle model cannot pass this sharp turn. We can see the result in the next video. And for the real experiment, we use a turtlebot as our guide dog, and we find the rigid rod, and myself as the I covered my eyes as the blind people, and the guide dog can guide me collision free to move to one place to another place. And some results I highlight here. So first, our model is able to deal with sharp turns, but the bicycle model will fail here. And our model is able to avoid previous unknown obstacles, our path planning algorithms. And we can track the human position accurately. The maximum modeling error is 0.15 meters. The mean error is 0.057 meters, and the error standard deviation is 0.031 meters. And next, I would like to share a video here. Yeah, first is the simulation test. So here is the simulation. This is use the bicycle model, and this has some unknown obstacle, so it fails here. So now it detects the unknown obstacle and it able to replan, and this is just a normal case. And this shows the examination here. Okay, and then next we goes to the real test. Yeah, it can pass through this narrow place without collisions. Okay, thank you very much.